Now that we've talked about the inverse trigonometric functions, I want to talk about how do you solve equations involving trig functions. And to start off with this kind of idea, I want to think about a fairly basic sort of problem that you could encounter like this. Let's suppose that we want to solve the equation sine of x is equal to 1/2. Okay, so this is a fairly reasonably short equation, but we need to be kind of careful about the solutions to it. Because if this were a polynomial equation, let's say, then we would know that there's a finite number of solutions. Every polynomial equation has a finite number of solutions to it, and that's it. But in this case, the problem is we need to note any solution can be shifted by multiples of the period of this function. In other words, if I shift this thing by a certain amount, then, or if I shift this thing by 2 pi k in particular, not just by a certain amount, but by 2 pi k in particular, if I have a solution, then shifting it gives me another solution. In addition to this, we're going to have to think about the fact that there might be multiple solutions within one period. So think about for a moment what this means. What this means really is that on the unit circle, give me a moment to draw a unit circle here. On the unit circle, the sine is the y coordinate. So we are looking for what are all the angles whose y coordinate is 1/2. Well, that's going to be all the angles that have this as their terminal point or this as their terminal point. So the solutions to this are going to be pi over 6 as well as 5 pi over 6. But it's not just those, it's also those solutions shifted by 2 pi k. So our answer to this is going to be kind of long, and it looks complicated, but it's not as complicated as it sort of looks at first glance. It's actually just saying, well, it's all of the angles that have these properties. So what we can say here is the solution is going to be that x needs to equal pi over 6 plus 2 pi k, or it could be 5 pi over 6 plus 2 pi k, where k is any integer. And this whole thing is our solution. We get an entire family of solutions, okay? Because we get these two different solutions over one period, and then we also have to shift those solutions to all the other cycles. Now, in general, if you have a problem that looks like this, there's kind of 3 different cases that you can get. And to understand those 3 different cases, we can think about the graph of the sine function. So in general, if I want to say sine of x equals c, where c is some number, then there's 3 possibilities. I want to think about what happens over one cycle, and then I want to think about what happens in general. So let's first of all graph one cycle of the sine function. Give me a second here as I mark up my number line, and then I'm going to graph one cycle here. There we go. Okay, now there are 3 kind of cases that can happen. One case is that over this cycle, the line y equals c hits the curve y equals sine of x twice. So we get 2 solutions per cycle. Another possibility is that y equals c. If we're dealing with c being plus or minus 1, well, in that case, we only go through, okay, that looks kind of not quite right because I'm doing a sort of a ugly drawing here, but you only hit it at one of its, at either the peak or at the minimum here, and so you only hit it once per cycle. The third possibility is that if c is bigger than positive 1 or less than negative 1, then you don't hit it at all. So we can kind of summarize these three cases. Case 1 is that minus 1 is less than c is less than positive 1, and then we get 2 solutions per cycle. Case 2 is c equals plus or minus 1, and that is 1 solution per cycle. And then case 3, let's just write case 3 down here. I do apologize again that this is such a small board for me to write on. Case 3 is if the absolute value of c is bigger than 1, then we get no solutions. Now, the thing that we want to kind of think about as well, though, is how can we get all of the solutions per cycle? Because in this last example, we actually knew what the angles are that were going to give me the solutions. The reason for that is because we knew for which angles sine gives you 1/2. But what if we don't know that? Well, it turns out that if we don't know what those angles are, we can write the solutions using sine inverse. If you don't happen to know the exact values for the angles, you can write them in terms of the sine inverse function. So I want to illustrate that procedure here. And as we do this, we're going to see something a little bit subtle happen that we need to think about. But I think the best way to explain what that is and how we deal with it is to just go through the problem, and you'll see kind of why we need to be a little bit clever about what we do with this. So let's suppose that I want to solve sine x is equal to, let's say, 1/3. Okay, I don't know what the answer to this is. I don't know what angles this would be. But what I do know is this. Actually, you know what? For the sake of being a little less confusing, let's just call this angle t instead of x. And we'll say that we want to solve for t. That way I can make my unit circle on x and y, and there's no confusions. Okay, so the point is, I'm trying to find what are the angles that have these terminal points, where this is the y equals 1/3 case. Well, one angle is going to be given by t equals sine inverse of 1/3. Now, that is going to be this angle here. That angle is sine inverse of 1/3. Here's the thing about sine inverse. Sine inverse is always going to be somewhere between minus pi over 2 and positive pi over 2. Here's the question then. What is this angle here, which is going to be my other solution? The other solution, if you think about it, this angle here, the one that kind of has the double arcs, is the same as this angle here. That's this angle subtracted from an angle of pi. So the other solution that we get is going to be t equals pi minus sine inverse of 1/3. These are our two basic solutions that we need to start with. So this angle, let's see if I can actually mark this out here. This is going to be pi minus sine inverse 1/3. Now, those are two solutions over one single cycle, but we now need to also account for the fact that I can shift them by multiples of 2 pi. So I can say, in total, we get t equals sine inverse of 1/3 plus 2 pi k, or it's pi minus sine inverse of 1/3 plus 2 pi k. And again, k here is just symbolizing any integer because I want to say, well, you can always shift this thing by a multiple of 2 pi k. Hopefully that makes sense. Now, if you didn't quite get that the first time around, I want to you should really go back, watch it again, and go through it carefully and slowly, because this is a little bit tricky stuff, okay? This is some little subtleties going on here that you really need to think about, and it's important to make sure that you really understand what's going on. So we can write down a general rule here for what to do if you have sine of x equals c with -1 less than c less than +1. Actually, this will even work for less than or equal to. It's just that in some cases, the less than or equal to is going to end up being redundant. But the rule that you're going to get is that your solutions will be x equals sine inverse of c and x equals pi minus sine inverse of c. Now, the reason for this is exactly what we just did. You're going to get one angle plus that angle reflected horizontally. Well, what happens when you reflect a horizontal? What happens when you reflect an angle horizontally? You basically just take that angle and you subtract it from an angle of pi. And that gives you the angle horizontally reflected. So these are our base solutions. Which is just kind of what I call them. I don't think that's an official name for them, but I like to think of these as our basic solutions over one cycle. And then you have to add 2 pi k to each of these, because you could shift all of these things over by multiples of 2 pi, and those would still be solutions that would still be fine, okay? So we do need to remember these are the basic solutions, and then you can always shift them by the period. So let's see if you guys can figure out this problem. So let's see, I want you guys to take a minute and see if you can solve 4/3 sine t is equal to, let's say that we want to say that this is equal to 1, just for this particular problem. So pause this for a minute, try to see if you can work this out, and then now we'll take a look and see how you can actually do this problem. So hopefully you were able to figure this out. The first step is going to be to simplify this to say that this means that sine of t equals 3/4, because I can just multiply both sides here by 3/4, and that way I have sine of something equals something. Okay, so the next step here is going to be to use what we just said. So we're going to have t is equal to sine inverse of 3/4 plus 2 pi k, or it could be pi minus sine inverse of 3/4 plus 2 pi k. So it could be, in other words, all of these values for t are going to work. Now notice I have to write this as just sine inverse of 3/4 because I don't know what sine inverse of 3/4 is in radians or degrees or anything like that. This is something that we don't know the exact value for that angle. If you threw this into a calculator, you could get a decimal approximation. And so if all you're looking for is a decimal approximation, that's fine. But sometimes you want to be able to write it down exactly. So I want you guys to get used to working out exact values for these things, even though in a lot of applications you might eventually say, hey, we want to go to a decimal approximation. Well, the thing is, you can always get your decimal approximation later, and sometimes you want to kind of keep things in an exact form for a while instead. So I think it's good, for the sake of practicing, try to get used to doing that. Okay, so we've seen how you can do this sort of thing, where in this problem we had to sort of simplify things a bit, just rewriting the problem to get this as some trig function is equal to some number. And once we're at that point, then we're kind of in a good place to solve this sort of thing. Now, what about if I gave you the problem 1/2 sine t plus 2 is equal to 0. I want you to take a minute to try to solve this one and see what you can come up with. Okay, did you come up with any kind of an answer? The answer to this one is actually, it's almost so simple, like it's almost too easy in one sense. You might think like, oh, this doesn't seem like it can be right. It seems like it should be more complicated. So the way that I would solve this is I would say, okay, this means 1/2 sine t equals -2. Just going to move the constant over. And then I can multiply both sides by 2. So I get sine t equals -4. Now, there's no problem with the fact that this is a negative number. That's perfectly acceptable. The problem is that the absolute value of -4 is bigger than 1. That means that this actually has no solutions. So like I said, you may have found that and then thought that seems like it's too easy. But yeah, that is actually the answer to a lot of these problems, is that there's no solutions. That's all there is to it. Now, we've looked at sort of some of the basic problems that you can deal with when you're solving equations involving trig functions. I would like to now take a look at a slightly more complicated sort of situation. And I want to think about, what do you do when you're dealing with this kind of a situation? So let's say that we want to solve sine of, let's say, 2x minus 1 equals 2/3. The problem here is that we've got this stuff inside of the sine function. In other words, instead of just having the sine function of a variable, we have the sine function of some expression involving the variable equals some number. So what do you do in this case? Well, the thing that we can do is we can think of this entire quantity as our t. And we can say, well, the solutions in general are going to be that t has to be equal to the inverse sine of 2/3 plus 2 pi k, or t has to be equal to pi minus inverse sine 2/3 plus 2 pi k. But this is actually what t is equal to. So we get a couple of possibilities. We get one possibility is that 2x minus 1 equals sine inverse of 2/3 plus 2 pi k. And that gives me x equals, this is going to give me sine inverse of 2/3 plus 2 pi k plus 1, all divided by 2. The other possibility is that I have 2x minus 1 equals pi minus sine inverse of 2/3 plus 2 pi k. And this is going to give me x equals pi minus sine inverse of 2/3 plus 2 pi k plus 1, all divided by 2. So, these answers look really long and complicated, and yeah, they are pretty big, but notice that we're only doing what we did in the previous problem, except that at the end, we remember, yeah, this is not what we're looking for. What we're really looking for is this number x. The angle that we're thinking about is written in terms of x in some way. And for this reason, we get multiple solutions depending upon, basically, in other words, you take the multiple solutions that you get, and then you solve those new equations for this original variable. So let's take a look at another example of doing that kind of thing and see what it gives us. Give me a moment while I erase all of this. What if, instead of the problem that we just had, what if I had sine of x squared equals -1/2? And by the way, we're going to talk about how do you deal with the other trig functions later. But I want to talk, first of all, about the sine function here and how to deal with it. And then once you understand all the subtle details that go on with sine, dealing with cosecant is relatively similar. And dealing with cosine becomes very similar. There's a few changes. We'll look at them later. But like I said, let's focus on sine for the moment. We will get to the other trig functions. So in this case, what we're going to do is we're going to say, okay, if this is some angle t, you could also call the angle theta if you want. I know we've been doing that. Also, give me one moment to pause this. I need to do something. Sorry about that. Answering somebody's question very quickly here. So we think of this as t. Well, okay, so we're looking at t equals sine inverse of -1/2, or and then plus 2 pi k, or it is pi minus sine inverse of -1/2, again, plus 2 pi k. Now, one nice thing in this case is that we actually know what this quantity is. Do you remember what it is? So this is actually -pi/6, which makes this 7 pi over 6. So what we get then is we get two possibilities for our angle inside of this trig function. And now what we want to say is this means that x squared is equal to -pi/6 plus 2 pi k, or x squared is equal to 7 pi/6 plus 2 pi k. This means that x is going to be equal to plus or minus the square root of -pi/6 plus 2 pi k. And here we need to have k. Let's actually, we'll think of this as a k still. And we'll say, in order to make this work, of course, k is going to need to be bigger than or equal to 1. Otherwise, we'd be taking the square root of a negative number. Or we could have x equals 7 pi/6 plus 2 pi. Let's call this j. And then we're going to be doing plus or minus the square root of this, which I did not leave myself enough room to do. And j needs to be bigger than or equal to 0, because otherwise, again, I'd be taking the square root of a negative number. So we get a lot of different possible solutions here, okay? But that's fine. And it's not very much different than what we did in the previous problem. You just have to remember that, hey, we're taking a square root, so that's going to mean that we're going to have to take plus or minus the square root in both cases. Hopefully that was kind of clear. All right. Now, the next thing that we want to think about is, what if instead of having some kind of weird thing inside of it, what if you had something like sine squared of x is equal to 4 over 9. So what if the squaring is actually for this function instead? Same kinds of ideas as what we've done before are going to apply here. So this is going to turn into sine of x is equal to plus or minus the square root of 4 over 9, and that becomes sine of x is equal to plus or minus 2/3. So I can really think of this as two possibilities. Either sine of x equals positive 2/3 or sine of x equals negative 2/3. Okay, that's a 3. That is a 2, as it is supposed to be, negative 2/3. And now I just have to solve these two equations, and any solution to either of these equations is going to solve the original equation. So take a minute and see if you can find all of the solutions to these equations. We're able to do it. So sine x equals 2/3. This is going to have the solutions x is equal to sine inverse of 2/3 plus 2 pi k, or pi minus sine inverse of 2/3 plus 2 pi k. And same kind of deal is going to happen on this other one. Sine x equals negative 2/3. Well, this becomes x equals sine inverse minus 2/3 plus 2 pi k, or pi minus sine inverse of negative 2/3 plus 2 pi k. So we get all of these families here that are possibilities. One thing that you might notice that is of interest, however, is you can actually consolidate these a bit. And I want you to think for a moment about why this is true. So notice that sine of minus x is equal to negative sine x. So that means that sine inverse of negative 2/3 is the negative of sine inverse of 2/3. So what does that mean? Well, that means that these are all really the same thing, except this one has a negative out front of the sine inverse. So we can really consolidate our answers into x is equal to plus or minus sine inverse of 2/3 plus 2 pi k, or pi plus or minus sine inverse 2/3 plus 2 pi k. Okay, now how important is it really to consolidate things like that? It's a good idea to know how to do this. I mean, you always want to know how to do this. Do I care that much? No, not particularly. I mean, if you left it like this, I would personally be fine with it. For the most part, I mean, I'd probably note on your thing like, oh, hey, you should make this simplification. Now, unfortunately, because of this whole online business, we're going to be mostly working with my math lab. So as you do the homework, check how they want you to enter these solutions. It might be a little bit complicated to figure that out for the first couple of problems, but they have plenty of examples in there that show you what format they want you to give it. And when you have that format, then you kind of know how much do you need to consolidate and simplify and things like that. Okay. So the last thing I want to talk about here is, what do you do if you've got a cosecant problem? There's a neat little trick if you have a cosecant problem that is going to allow us to turn any cosecant problem like this. Well, okay, probably somebody could cook up something nasty where this trick would not be so useful. But basically, here's what you should think of trying to do if you see a cosecant problem. Remember that cosecant of x is 1 over sine x. It is the reciprocal of x. So let's suppose that I ask you to solve cosecant of t equals 4. We could try to do this by using cosecant inverse, and it actually wouldn't be too bad. But you would have to work out the rules for going between, like finding all of the solutions for cosecant. Well, this is equivalent, though, to solving sine of t equals 1 over 4. In other words, I just take the reciprocal here, and I turn it into a problem involving t. Of course it involves t. It already involved a t. I turn it into a problem involving sine instead of cosecant. And now I can do this just the same way as we did before. And that will work even if I have something more complicated here. If I have a problem like cosecant of 3t squared minus 1 is equal to negative 2, well, this is the same as saying that sine of 3t squared minus 1 is equal to negative 1 over 2. Okay, so 3t squared minus 1, this is just some crazy angle. That means I can take the reciprocal on both sides and I can turn this into a sine function. And now we're back in the boat where we were before, where we're just dealing with sines, okay? So, if you can handle sine function equations involving the sine function, I guess I should say, then you kind of get the cosecant equations for free, if you remember that you can do this kind of conversion. All right, so the next time what I want to do is to talk about what if you're dealing with cosine or tangent. Turns out that cosine and tangent, once you get the hang of dealing with sine equations, those cosine and tangent problems are pretty similar. Now, there's some differences, and that's what we're going to talk about, but kind of a similar idea. And once we get cosine and tangent down, by doing similar tricks to the cosecant to sine trick, we can get secant equations to turn into cosine equations, and we can get cotangent equations to turn into tangent equations. So that's what we will be doing in the next video.